Hello everyone, we are Team 10. ExxonMobil consists of Arista Ambari, Aurel Horinisha Sutomo, Kayla Fauzia, and myself, Shivan Noraini. In this opportunity, we will present the result of our paper summary with the title Using Artificial Intelligence to Predict IPR for Vertical Oil Well in Solution Gas-Derived Reservoirs, a New Approach. Well inflow performance relationship or IPR has a wide range of applications in both applied and theoretical sciences, especially in the petroleum production engineering. So what is IPR? IPR or well inflow performance relationship is the relationship between oil production and flowing bottom hole pressure. The curve that shows the relationship is called the flow characteristic curve or the flow dynamic curve. Why an accurate prediction of well IPR is very important? An accurate prediction of well IPR is very important to determine the optimum production scheme, design production equipment, and artificial lift systems. What techniques did they use to predict oil well IPR in solution gas derived reservoirs? According to the paper, they used backpropagation network or BPN and fuzzy logic or FL techniques to predict oil well IPR in solution gas derived reservoirs. The models were developed using 207 data points collected from unpublished sources. Statistical analysis was performed to define the more reliable and accurate techniques to predict the IPR. According to the results, the new fuzzy logic well IPR model outperformed the artificial neural networks or ANN model and the most common empirical correlations. The methods that they used to evaluate the model's results are the average absolute error, least standard deviation, and highest correlation coefficient. The proposed fuzzy logic well inflow performance relationship model achieved an average absolute error of 1.8%, standard deviation of 2.9%, and the correlation coefficient of 0.997. So the benefits of the developed technique is it will help the production and reservoir engineers to better manage the production operation without the need for any additional equipment. It will also reduce the overall operating cost and increase the revenue. Productivity index, or we can symbolize it as J, is the ability of a well to produce, or how many barrels can be produced by a well per 1 psi drawdown. Productivity index can also be defined as the ratio of the total liquid flow rate to the pressure drawdown, which can be expressed by the formula below. PR stands for average reservoir pressure, PWF is flowing wellbore pressure at a defined rate, and QT is total flow rate including oil and water. Next, on top of the right, we have the plot of the flowing wellbore pressure or PWF versus the total flow rate or QT, and a straight line with a slope of -1 per J. The graphic above represents the relationship that exists between the flow rate and bottom hole flowing pressure, that is called as the inflow performance relationship and revert as IPR. Several IPR correlations focus on the graphic of the inflow performance relation in case of solution gas derived oil reservoirs in which bubble point pressure equals to reservoir pressure.
Hello, my name is Kayla, and I'm going to continue the explanation on empirical correlation for IPR prediction. So, in this part, we examine six commonly used empirical correlation developed to predict the inflow performance relationship or IPR in vertical oil wells. So, the correlations are first, Vogel's correlation, which was based on a computer generated IPRs for a saturated oil reservoir. It performs well in the early stages of production, but it deviates as the reservoir depletes. The next one is with Kovic correlation, who proposed a pressure rate relationship derived from multi rate tests and gas well behavior using a flow coefficient and a back pressure exponent. The next one is Clint and Majors, who modified Vogel's model by incorporating changes in the bubble point pressure to predict future IPRs more accurately. Next is Huygens correlation, who use a simulation-based models involving fluid and relative permeability data to generate a new IPR correlation. Next is Elias et al. Correlation, who introduced a pseudo steady-state correlation considering the effects of average reservoir pressure on oil mobility. And for the last one is Kasanoff et al. Correlation, who developed an IPR model similar to Vitkovich, but used two exponents to better describe inflow behavior in solution gas drive reservoir. Next, I'm going to explain about the artificial neural network or ANN approach, specifically in the backpropagation network or BPN used in the study to predict IPR for vertical oil wells in solution gas drive reservoir. So, artificial neural network is the tool used to recognize and determine the classification of complex system which can't be achieved using human brain. So, basically, ANN is particularly useful for recognizing and classifying complex nonlinear system which cannot be modeled effectively by traditional empirical correlation. So, the model implemented here is a backpropagation network or BPN with two hidden layers. As for the input variables, included bottom hole flowing pressure, gas flow rate, and also APR gravity. And the output is oil flow rate. So as shown in the graph and table, the ANN model achieved high correlation coefficient and acceptable error rates, which indicates that ANN not only fits the training data, but also generalizes effectively to unseen test data, outperforming traditional models like Vitkovich.
Good morning, good afternoon, and good evening for Mr. Ardian. My name is Aris Tambari, and now I'm going to explain about how the fuzzy logic technique works. That the fuzzy logic technique works by using multiple input and output variables, and it is especially useful when dealing with uncertain or imprecise data that do not have clear boundaries. In the previous studies, data from 16 different reservoir models were used to build various AI models. Among them, the multi-layer perceptron or MLP model gave the best results, especially when using one or two hidden layers. It showed consistent performance in both training and testing phases. The study also applied NGP or genetic programming and achieved excellent accuracy with prediction errors as low as 0.2% and 3%. Other advanced models, such as NFIS and LLNFM, were tested on horizontal wells and also performed better than traditional empirical models. Then, this research collected 207 real well test data points from vertical oil wells with solution gas drive that proves that fuzzy logic and other AI techniques can provide more reliable and accurate prediction of reservoir engineering. Okay, next on this slide, this is the given data that used to train and test the AI models. A total of 207 well-test data points were collected from vertical oil wells with solution gas drive. This data were divided to 70% for training, 15% for validation, and 15% for testing. This split helps ensure that the models are well trained, properly optimized, and accurately tested on new unseen data. The input parameters included bottom hole pressure or PWF, PR, reservoir pressure, oil and gas production rates, that is QO and QG, and API gravity. With this complete and diverse dataset, the AI models like ANN, fuzzy logics, and ANFIS were able to learn the complex patterns in the data and provide more accurate IPR prediction than the traditional methods.
So I will explain about the result and discussion for the artificial neural network or ANN model is built with two hidden layers. Three main inputs are used: bottom hole flowing pressure, gas flow rate, and epic gravity of oil. The AN the A&M model provides fairly good result with a high correlation 0.991 to the actual data. However, the average Pearson relative error or APRE reaching mean 12.67% and a maximum deviation of 112.87 suggests that the A&M predictions are not yet stable enough, especially when tested on unseen data. This indicates that although the ANN can recognize nonlinear patterns, the model is still susceptible to overfitting or lack of generalization. Next, fuzzy logic, built using Adaptive Neural Fuzzy Inference System or ANFIS. In contrast, fuzzy logic demonstrates significantly superior performance, with an array of only 1.22%, a low standard deviation 8.86 and a high correlation 0.995, Eval has proven capable of providing more accurate and consistent prediction. The advantage of VFL lies in its ability to manage uncertainty and data variation through a fuzzy logic approach, which is more flexible compared to pure mathematical models. Meanwhile, the Felkovich method as an empirical model shows significant limitation, although useful in some conditions. Its results deviate considerably from the actual data, especially under bubble point pressure. This indicates the empirical model are less capable of capturing the complex stability of two-phase flow occurring in solution gas reservoir. Next, for a conclusion, in the study, two artificial intelligence models, ANN, which is BPN, and Eval, which is AMPHIS, have been compared with empirical correlation to predict the inflow performance of vertical oil wells producing two-phase flow. 207 points data sets have been run in different bottom hole pressure conditions. 145 points data sets have been used for training. The rest were used for error checking and performance testing. The results show that the EVA model results in the smallest error for unseen data when compared with the other intelligence model and Fedkitch model. That concludes our presentation. Thank you for your time and attention. We hope this presentation has been insightful. Assalamualaikum warahmatullahi wabarakatuh.